I will move on to the next problem. Yeah, similar quadrilaterals are hard. Oh yeah, I love similar quads. So we draw the circumcircle O and orthocenter H. O is the center. And then an arbitrary line through H. That's interesting. So let me do this first, just so that, okay, so E is on a C and F is on a B. And then we draw the circumcircle of AEF. And it meets, I gotta be careful about clicking. So it meets this at N. T is the intersection of A, J. So J is the center of that circle. I don't want H, I want J. And P is the intersection of AJ and EF. Let's draw this a little better. We want to show that NP and AO intersect at J, which is really just the same as saying angle ANT is 90 degrees. Wait, is this trivial? That's just the same as showing that ANT is 90 degrees, right? Which is the same as showing AET and AFT are 90 degrees.
Well, T is the intersection of AJ and EF.
Oh, AJ, oh, and EF, sorry. So not this, whoops. T. Okay, so we want to show angle ANP, but NP doesn't meet, oh, on this circle, my bad. Okay, that's kind of interesting. N is this, yeah, so a spiral similarity takes NFB to NBC.
Intersect AO with AEF, circumcircle of AEF.
Yeah. So we want to show N and T are collinear with that point. So it almost, okay, no, T is not the midpoint of EF. This looks a little like Sharky Devil, like but it's not really. So what's a good way? Can we show angle NDA is angle TDA? Or, yeah, what do we know about point T? So I wonder if, because we know NFE is similar to NBC. So what does H correspond to here? And what does T correspond to? So I wonder this spiral similarity that takes NFE to NBC. I wonder what it takes A to. So how do we find that point? I guess we draw the isogonal.
I haven't proven yet, but it seems like AT passes through the anti-Steiner point of EF.
AT passes through what?
The anti-Steiner point of line EF.
Anti-Steiner point.
Yeah.
Okay. So that lies on this circle, right?
No, I mean like if you reflect EF over BC, EF over AC, and EF over AB.
Okay.
Yeah, and the three lines concur at the anti-Steiner point of ABC.
Okay. So if you take EF and you reflect it over, well, if you take EF and you reflect it over BC, that's just a reflection of, so you're saying reflect this about the three sides?
Yeah, that point right there. I'm not sure if this is helpful, but yeah, I just accidentally see it.
Okay. And then Hakan says, it seems like FJE and AT concur. Yeah. Interesting. So what I was thinking was, let me try this. I want to see like the spiral similarity that takes NFE to NBC. Where does it take NA to? So basically I want an angle. Yeah, let me do this. So Okay, I'll need to take the angle bisector of this and then reflect NF over it. This is a little annoying, but okay, so I'll call this A prime. And then I'm going to delete a bunch of stuff. So I think that's good. So the spiral similarity takes A to A prime. So NAEF is similar to NA prime CB. And so basically, if we let let's hide this one. Okay, so AJ would correspond to A prime O. Yeah, so that's the antipode of this point. Okay. Yeah, you can write it out and then I'll paste it as the proof. I've been more and more okay using trig as the channel goes on. But yeah, it's interesting. This anti-Steiner point is if a spiral similarity takes A to A prime, then that is the antipode of A prime. It looks like. Yeah. So and then to show that NT meets AO on the circle, that's the same as saying that angle FNB. So FNB is FNT, but FNT is the same as BN. So we got to label this point right here. BNI. So can we show that BNI equals a so basically oh yeah, sure. So did you see so for Con, were you here when we started the problem, or basically G is the anti-Steiner point of EF, and we saw that AT passes through it, and then also we found that if we let a spiral similarity take, so a spiral similarity takes NFE to NBC, so if that same spiral similarity takes A to A prime, then it turns out that A prime is the antipode of G. So we're trying to prove all this. So we want to show, let's see, we want to show FAD. So that's very easy to calculate, angle FAD. That's like, I think that's just 90 minus C. We want to show that's FNT, which is the same as BNI. So we want to show BNI is 90 minus C.
Then it is the same as saying NI meets AO on the circle, is it?
NI meets AO on the circle.
The big circle.
The big circle. So that's the same as saying angle ANI is a right angle. So yeah, that's kind of the same as saying that NI and this point are collinear, right? That the antipode of A on the little circle. Yeah, it doesn't matter.
Wait, did we prove the fact that AT and the anti-Steiner point are collinear?
No, we didn't prove it.
Then okay, so I think we should draw it out, or maybe define G in a different way.
Define G.
Did you say G is the intersection of AT and the circle?
Okay. Yeah, we could define it that way, and then we try to show it's the anti-Steiner point, is what you're saying.
But I don't know if the anti-Steiner thing is helpful. I'm just, predicting. And
Yeah. I introduced the orthocenter of AEF. We can prove G lies on AJ by an angle chase. How do we do that? Yeah, G's the anti-Steiner point. Okay. So yeah, maybe I should delete A prime because I don't think you guys are using A prime in your solutions. G, E, and L, and M, F, and G are collinear. Okay, let me, yeah, the figure is too messy. So yeah, I'm gonna make it a little easier. Can I delete A, or at least hide it so it's not, okay. Okay. So by Pascal's theorem, let's think about this. So L, G, E, and L. Wait, how do we? Don't you need like how do we know G, E, and L and G, F, and M are collinear? Like, don't you need 2 out of the 3? In other words, we know that B, L, and CH. We know that B, L, and CM intersect on EF. But don't you need like 2 out of the 3? By Pascal, we know MF and LG concur at G. prime. Yeah, let me hide this actually. Wait, how did you, oh, so since MF is a reflection of E with EF with respect to AB. Okay. So really it's like first we draw GF and GL and then and then we can show, okay. Yes. Hold on 1 second, GeoKing. I want to see if they can finish this way. But yeah, that's an interesting idea. ARH, AJO, NJO, and FB. That looks like it could be true. So angle FAJ equals 90 minus AEF. Okay. So let me copy this here. So let me start. Let G. So I'm gonna. And then let CH and BH meet the circle at M and L. Let BH and CH ABC at M. And then so FG is a reflection of EF over AB. I don't think we need Pascal. Do we need Pascal at all? Or is that just like an angle chase? Yeah, implies MF and G are collinear. L, E, and G. And then once we know that, because that would be an angle chase because, yeah, FMH and EHL are isosceles basically. So, Yeah, because FMH and FEL are isosceles, so that proves it. All right. And then we have that. So FAJ is equal to BAG. FAJ, it's 90 minus AEF, which is ELH, which is HLE, which is BAG. So A, J, and G are collinear. Is this Serdar's? Yeah, that's Serdar's proof. Okay. So okay, once we know A, J, and G are collinear, then does that help solve the problem?
How is 90 degree minus AEF equals EHL?
Sorry, say it one more time.
How do we have 90 degree minus AEF equals EHL?
Let's see. So AEF is half of LEH. Yeah, because EHL is isosceles, and this is like.
Oh, so I didn't see. Yeah, the isosceles.
Yeah. By the way, E equals AEH. So Serdar just wrote a proof. We want to prove that DF over DE equals HE over HF times AF over AE. Once we know that A, J, and G so if we reflect G over O, okay, DE over DF, I'm trying to understand Serdar's proof. So we want to prove that DF over DE equals TF over TE times NE over NF. Okay, yeah, that would, I remember that lemma. So FMH, oh, that's just because, so we define G to be the anti-Steiner point. And so basically FM and FH are, FM is a reflection of FH over AB. So that's why it's isosceles. Yeah. And okay, so I see Serdar's proof using trigonometry. So you try to use that lemma. If we can show that DF over DE is TF over TE times NE over NF, then that would prove that NT and D are collinear. NE over NF is CE over BF. And so yeah, I'm just going to paste what Serdar put in the. So yeah, it looks like Serdar has a complete solution. But yeah, uses a little bit of trig. Okay, yeah, let's see. Yeah, let's see if we can solve it this way. So but yeah. So I'm gonna let G prime be the antipode of G. And then I want to show a spiral similarity takes if I can show a spiral similarity takes about n takes AF. Yeah, can I show that triangle AFE is similar to G prime BC? Because that would solve it if I could show that. So we have G prime BC. G prime BC is is 90 minus GBC. And GBC is GAC. Wait, hold on a sec. I think I might have this. G prime BC is 90 minus GBC, which is 90 minus which is 90 minus F. Yeah, okay. I think I got this. So let G prime be the antipode of G. And now I claim that G prime is the image of the spiral similarity of A with respect to N. So we have G prime BC which is 90 minus GMC. Which 90 minus GMC, because this is isosceles, that is angle AFE. And so if that's true, then similarly G prime CB is AEF. That means that triangle G prime BC is similar to AEF. Or AFE. And so basically that means yeah, that pretty much solves it, because then N, F, E, and T corresponds to basically A, N, F, E, and J correspond to G prime N, B. So yeah, we have A, N, F, E, with center J is similar to G prime and BC with center O. And then once we have that, then it's just an angle chase, because we want to show that NT and D are collinear. But I thought I solved it before. So we want to show that angle DNF is TNF. And like, how did I do this? I'm getting confused. I thought I had this before. So we want to show that angle FNT is FND, but FND is FAD. Okay, and FNT is BNI. Okay, so FAD, sorry, FND is FAD, which is 90 minus C. So we want to show FNT, we want to show BNI is 90 minus C. Which, yeah, we could. So BNI is 90 minus C. Oh, you know what? Yeah, maybe I'll just use Serdar's trig proof and move on. Just because, yeah, it's already 11 a.m. So yeah, here's Serdar's proof. I'm just gonna, yeah. Okay, so let me copy Serdar's proof just for the viewers on YouTube. And then I'll move on to the next one. Okay. What happened here? Oh, I don't want to do either of these. Look at that, the whole proof fits right up here. Just move this down a little bit. All right, so that is the proof. And I will move on to the next one. Whoops. I wish you could make this, there probably is a way to make this smaller, but yeah, there, now you can see the whole thing. All right, so this is the third problem from the Vietnam IMO training. And, whoops. Okay. So we have a triangle ABC and a circle O. And M and N are the midpoints of arc BC. What is M? So N lies on arc BAC. Are they the midpoints of both of the two arcs? That's what I'm guessing. So this would be N, and the other one would be M. It's just a guess for now. I'm not 100% sure. So if this is M, and we want to draw the mixed linear circles of AMB and AMC. Interesting. I don't know, Khan, can you confirm that this is the M that they actually wanted?
Yeah, you got the positions right.
Okay. So what I'm going to do, let me draw the mixed linear circles. Let me think of the best way to do this. So I'll try to do it like this. So I'm going to draw the incenters of BMC and BMC. Whoops.
It is mixed linear.
Yeah, I'm going to draw the mixed linears. I'm just using these to help me draw it. So, actually, let me.
Is it with respect to A or M?
Mixed linears. Oh, I just assumed it was with respect to A, but I actually don't know. Khan, do you know? Is it the mixed linear with respect to A or M?
Let me check real fast. Wait.
Okay.
Yeah, it is with respect to A. Sorry.
Okay, it's all right. So, oops, sorry. Let me close this. So I'm gonna label these 4 points. Okay. So the circle should pass through this and this. And then also, we draw KF, we want to see where KF meets the side.
I think J and K are the center of the mixed linear circles.
Oh, really?
Yeah.
Okay. So, all right, so let me draw the circumcircles of A and B. Well, we already have the circles, but no, because it has to be tangent to arc BC, right? So J couldn't be the center. Or I think it's the point of tangency is what you mean.
I mean, you mislabel it. Like originally, J and K are the.
Oh, yeah, I see what you're saying. The letter is different. The letter should be like, yeah. And then let's see. This is the midpoint of arc let me draw the perpendicular bisector of AM too. And then I think I'll have enough to, so, sorry, I see the chat. People have written stuff. Basically, yeah. Hold on just a second. Let me first draw one of them and then I'm going to draw the other one. So I just need to see where this meets AB and this meets AM. And that should be the circle. So this point and this point right here. Oh man. Come on. There we go. Okay, so KPL is one of the circles, I believe. No way. I did something wrong. What did I do wrong? Oh, I need the midpoint of arc AB. Whoops. So yeah, K, I didn't do that right. Okay, I think that should be it. Whoops. Who knows though, maybe I messed up somewhere. P, L, there we go. And then I need the midpoint of arc AC. Oh, I have that, that's F. Oh, but I want to draw, sorry, I want to draw QF, and then I want to draw this point actually. Look at how hard it is to draw mixed linears. Only there was an easier way in GeoGebra. And then I think that should think so. If I'm lucky, this will be it. Now, what did I do wrong here? Oh, I need this point right here. So QF meets AC. Whoops. I need the point where QF meets AC. It won't make it easy for me. This. There we go. And now there we go. All right, finally, after all that work. So I could delete. I drew a lot of stuff here. So let me hide it all. At least most of it. Definitely don't need those two. I'm gonna, yeah. Is that good? There we go. Doesn't that look so much better? Okay, so now J and K are the centers. I was gonna say, that would be really weird if it lied on BC. Okay, J and K. And then we draw the the common tangent. Oh boy, we're gonna see a whole bunch of tangents here. So the inner common tangent. So I'm gonna have to hide a bunch. It meets MN. Oh, let me unhide N. At X. I'm not 100% sure that is N, but prove that the circumcircle of A XN is oh, it looks like it is tangent to both of them. That's interesting. Is it? No, I don't think that's. So is N a different? Let me check the chat. So a mix. A. Okay, I should intersect BD. But wait, this. I don't think N is right. So N is supposed to be. Yeah, can you? Oh. Khan, do you know where I went wrong in this problem?
I don't know, but the original, I think I translated it right. Pretty sure.
Okay.
Did you draw the inner tangent right?
Yeah.
Oh no, you just drew the mixed linear circle. Look at how you draw the mixed linear circle of AMC. Like it isn't tangent to AC.
Oh, you're right. So you are 100% right. So let's see, what did I, oops, sorry. Q. Okay, so I want this to be, okay, I think F is, because I need the midpoint of arc AC. I think that's what I did wrong. Yeah, U is the wrong point. Whoops. But yeah, I should delete that. Okay. And I want this point. Okay. QST. There we go. And now I want to draw the common tangent. Sorry, this took a long time to draw the diagram. Okay. I think we finally got it. So if this is X, then AXN. Perfect. That's cool. I like this problem. Okay. So let me hide this, And this. Yeah, it's actually not that, it's a hard diagram to draw in GeoGebra, but it's not that hard. Once you've already drawn it, it's not that complicated. Interesting. So I wonder, yeah, we don't know its tangent yet, but let's say we did. Is there anything special about those points? Are A, W, and U collinear? No.
As you
Okay.
said, maybe we can find special points W and Z, and we try to prove that these 5 points are cyclic.
So we can find a special point on this circle, is what you're thinking?
No, we will find exactly what W and Z is.
Okay.
It seems like AM passes through the point of homotopy taking J to K, like the inner homotopy center.
Oh, this point?
Yeah, maybe we can call the yeah, we can call it point. Maybe it will help.
Okay.
But I haven't proved it yet.
Well, we kind of know that. So the center of homophily is the intersection of the of the internal tangents, right?
Yeah, true. But we don't
This
know
is the
AM
definition.
passes through it. Oh wait, the AM is the common tangent. Yeah, right. That's
Yeah.
right. Sorry.
It's all right. So J, H, and K are collinear. Yeah, this one looks hard. The center of AXN, yeah. A, B, C, I'll just call it D. So yeah, we'd have like a little triangle here. Maybe it's worth drawing the center of ABC too. So that's O. The segments of DJK. Yeah, I can delete it. Yeah. DH, JZ, and KW will concur. DH. BH. How did you find that out? Or is that like Monge's theorem or something? Oh. Okay, it follows by Cheva. Well, what would, okay, because yeah, JH over HK. Yeah.
Can you intersect PQ and JK?
PQ and JK.
Yeah.
All right. Maybe it lies on.
Maybe it's on WZ. Can you draw it also? And AN.
AM. Yeah. Yeah, looks like it.
And also WZ.
Ah, wow. So yeah, we don't know yet that W and Z exist, but maybe this will help us figure out why they exist.
I guess we will apply a bunch of Monges. Let me think.
Monge's theorem.
The collinearity of BWZ comes from Monge's theorem.
Okay.
But I'm not sure how to do FAN.
Okay, but you know that these other three are collinear?
Yeah, the intersection of PQ and JK is the excimal center of J and K by Monge.
Okay.
Also, F is the excimal center of J and K. W, but we don't know
Yeah, we don't know W and Z.
we don't know the existence of W and Z. Yeah.
Yeah.
Is WZ parallel to BC?
Is WZ what? Parallel to BC?
Yeah.
I don't think it is. Although, let's see. Maybe it is. Yeah, how would I check that? So I guess I could draw the parallel. I could check it this way. No, it's not. It's close though. why does the x similocenter lie on AN? And is JK, is FJ the angle bisector of this? Okay, it's not the angle bisector. So the three other problems I chose were Komal. Do you wanna take a look through them? This one I looks pretty hard to me.
It's okay for you.
Oh, what?
It's okay to look at others.
Okay. Yeah. Oh, Geo, King, you wanna keep trying this one? I'm just gonna do the others just so that but okay, so let's see chat. All right, so we have a triangle ABC. The feet of the altitudes are A1, B1, C1, and then okay. So yeah, really, it looks like we only have to do this. Okay, okay, we do need all the altitudes. So yeah, basically if it's just saying we look at these. So A, B, C1, A, B1, C1. So those are just the circles with diameters A, B, and AC, right? And A, B1, C1, and B, C1. Is that right? Wait, that doesn't look symmetric. Wait, A, B1, oh, whoops, that's the wrong circle. A, B1, C1, and B, okay, really, yeah, I didn't, C should be at the top, the way they did it. So, C, A, B. A, B1, C1, and B, C1, A1. So these are points P and Q. And we want to show that AQ and BP intersect on the Euler line. So this is H. And then center of this is O. So it's saying that we want to show that AQ, BP, and OH concur. Oh, Komal. Yeah, Komal's a Hungarian magazine. And yeah, it has all different types of problems. So let me rename these A1, B1, and C1 just to match the problem. Yeah. So their website, I wonder if this is the 9-point center. So like the midpoint of OH. No, it doesn't look like it is. That's kind of interesting. So we know that PH and the midpoint of AB are collinear, right? And we also know that QH and F are collinear. I don't know if that helps. So yeah, PHE and the antipode of A are collinear, and QH and F and the antipode of B are collinear. Check the chat. Thanks for joining, Anmol, by the way. Yeah, P and Q are the Q points. F and Q are inverses with the circle with center H and radius HA1 times HA. So are P and E. So PEFQ is cyclic then? Is that true? Yes. Are those tangent to the circle? I don't think they are. I would be very surprised if they were. Yeah, they're not. I'm going to delete D. So yeah, it feels like there's some homophily because whenever I show something lies on OH, like maybe it's better to let those two lines like intersect at a point and then show that there's some homophily that takes one to the other. So is H the center of a circle? Like suppose HD and O were collinear, then there would be some homophily. that would take O to H around D. And what would it take A and B to? Let's see, is H the center of some circle? Some special. It is equivalent to HFA1 and HEB1 intersecting on HO. So it suffices to show that HO is the radical axis of those two.
Wait, this is just Pascal. Use it one time and you're done, I think.
Pascal's theorem?
Yeah, this one is pretty easy, to be honest. So can you draw the antipole of A and B?
Yeah. One sec.
Let's call it A prime and B prime, yeah. So we're gonna have B prime, HQ are collinear. And similarly, AP and A prime, I prime and HP.
Yeah.
So we're just using Pascal for AA prime, BB prime, PQ, and then we're done.
Yeah, you're right, it is easy. Okay. So I'll write it up. So let A prime and B prime be the antipodes of A and B. And then I'll just say P is a Q point implies PH, or let H be the orthocenter. So P is a Q point, so PH and A prime are collinear. Prime. All right. And so then we use Pascal's theorem, and that pretty much solves it. So by Pascal's theorem on PBA prime, BA prime Q, I'll just say AQ, BP, and OH concur. All right, let's check out the next problem. But yeah, that was a quick one. All right. So this one's kind of interesting. So this one is a tangential quadrilateral. So it's the fastest way to draw them. So here's usually how I like to draw them. We have one ray, we have another ray. Draw the angle bisectors. Actually, you know what? There's probably the fastest way to do it is this. Start with a triangle. Draw the end circle. And then just pick a point and then draw the tangents at that point. And there we go. So this should be A. And that should be B. Hide the rest. I'm just going to draw the rest of the figure before I hide stuff. So P and Q. So yeah, maybe it would be better if I like rotated it so that like kind of like this. There we go. So it intersects at BP. So this is P. And this is Q. And then UV is the diameter perpendicular to AC. Ah, this is interesting. This problem feels kind of familiar, to be honest. So U, this is U, and this is V. And we want to show that AC, so let me hide stuff. Hide this. We want to show AC, PV, and QU concur. Isn't this a fun problem? It's pretty simple to state, isn't it? So we have about 14 minutes. Let's see if we can do it. Make it bigger, a little bit bigger. Call that point F. I think we might have done this before. I don't remember. We used the SARS. PV and QU. Does BU and BV concur on the circle? Let's see. No, but it looks like it concurs on AC. So yeah, that's kind of interesting. So yeah, maybe it's worth trying these points.
Can you call out the tangent point?
Yeah, sure.
Can you check if the four line JI, KL, UV, and PQ are concurrent? No, I mean JI, like.
Oh,
Yeah.
okay.
You gotta draw the line.
All right. JI, KL, UV. I'm gonna move it over in just a second. Let's see. Ah, looks like they are. Good observation. Let me.
Yes, if they are, then I think AC is the polar of the concurrence point, and also the intersection of PV and QU is also lie on the polar of it, so it must be collinear. So we just need to prove they are concurrent.
Okay. Let me. Yeah. Let me try to make the best diagram I can. Like that. So yeah, it looks like a lot of stuff with poles and polars would help. Because yeah, it lies on the polar of A, the polar C. Maybe I could shrink the diagram a little bit. So yeah, is it clear that JI, BD, and LK concur? That feels like it should be like a well-known fact, right? Well, because if JI and BD concur, I wonder if we can use cross ratios. So yeah, so I think basically, if we let JI cut BD at M prime, then basically by Menelaus, we would have like M prime B over M prime B times BJ over JA times AI over IB equals 1. And we get the same one, like AJ is equal to AI and BJ is equal to BK. We'd get the same ratio when we do it on this side. And so yeah, JI, LK, and BB concur.
And also we can prove that UV passes through M because we have M lies on the polar of A, C lies on the polar of M lies on the polar of A and M lies on the polar of C. So we have AC is the polar of M. So EM is perpendicular to AC. So
Okay.
also we have EV is perpendicular to AC. So UEVM are collinear.
That makes sense. And then once we, so first I'm gonna write that all up. And then once we know those all are concurrent at M, is it like, how do you then show that these concur? Okay.
So we show, okay, you just type it out first.
Yeah, sure. So let JI intersect BD at M prime. So I'll just say label the tangency points as shown. Then by Menelaus, M prime D B, and then BJ over JA and AI over IB. Is equal to ID over BJ. And then similarly, if KL meets ED at M double prime, then M double prime D over M double prime B is equal to, that would be LC over KB, LC over BK. And that means that M prime equals M double prime equals M. Okay. So then M lies on the polar of A and C. So M lies on the polar of both A and C. That means that AC is the polar of M. And that implies that MU and V are collinear. Okay, so I did all that. And so what's the last step?
The last step is we have I think we have let's label the intersection of PV and QU.
Okay, PV and QU. Hold on one sec.
So by Brocard's polar theorem, N lies on the polar of M,
Okay.
which is AC.
So that solves it. So let N equal PV intersect QU. By Brocard's polar theorem, N lies on the polar of M, which is AC. So then AC, PV, and QU all pass through N. All right. So we have about 2 more minutes. Let's just PV and QU pass through N. And yeah, I'm sure there was a way to, because Menelaus, anything that you could do with Menelaus, you could do with projective geometry. So there's probably a way where I could have avoided that. But still, it's interesting. All right, so let's see. Let me just draw on that segment. All right. So I chose one more from Komal. Yeah, I don't think we're gonna finish. We're gonna get to it. So let me just take a look at it. So we have a cyclic quadrilateral ABCD. And then we see where do A, B, and C, B intersect, and B, C, and A, B. So P and Q. Then we take the theta of the perpendiculars from P to B, C, and A, B. Okay. This actually looks kind of familiar too. I'm just going to draw it. Let me make it a super small diagram. So perpendiculars. All right. A, B, and C, D, P to. So we draw that, and then we draw that, and that. So F, that's F. Okay, and then here would be the segment PQ. So we want to show that, so F, well no, F is actually, I'm not even going to relabel the points. So F, so P to BC, and N is Q to CD. So is it really those points? And this, okay. I am a little confused here, but we can look at this another time. All right, well, thanks everyone for participating on this session. We had a good group here today. And for everyone watching, if you'd like to join future sessions, feel free to email me at mgreenb801@gmail.com. The sessions are on Sundays at 8 a.m. US Central Time. And the email is going to be in the description of my video. So thanks for watching and have a good day.